Hello viewers, in this lecture we continue discussion on the instruction set of 8051. In the last lecture I have introduced to you the various aspects of instruction set, the instruction format, addressing modes. After that we have discussed the data transfer instructions, and today we shall discuss other categories of instructions like logical, arithmetic and control transfer instructions. But before I discuss the logical, arithmetic or control transfer instructions, let us have a quick recapitulation of the data transfer instructions which we have discussed in the last lecture. As you have seen, in this data transfer category, you can transfer data from the external program memory by using two addressing modes, that is your indirect addressing using best register plus index register indirect addressing modes. And as you can see here, since the data is coming from ROM, it is coming only to the register, that means the accumulator. These are the instructions. Move C comes to A at the rate of A plus dptr, that means data pointer and program counter acts as the base registers and accumulator acts as the index register. And here you see it takes, although the instruction size is 1 byte, it takes 2 machine cycles requiring 24 clock cycles. And then you can also transfer data from external data memory, as you have seen, by using indirect addressing, where you can transfer from say 00 to FF or in binary in decimal 0 to 256 byte by using indirect addressing using R0 and R1 registers, and the instruction format is move X at the rate RI A. And in this case, of course, since it is RAM, internal data memory, data transfer takes place in both directions. And also you can transfer from any byte in the program space by using this data pointer as the register, register pointer register. In this case also the address space can be from 0000 to F0000 to FFFF. So in this case also the direction of data can be either from register A to the internal or external data RAM, or it can be from the external data memory to the register A. And these are the instructions: move X, external data memory. So by using either registers, I mean R1 and R2, or data pointer. So you can see here it can be from external data memory to A or from A to external data memory. So you have two different types of instructions. Then we have discussed the various categories of data transfer that take place in the context of I mean from accumulator and to internal data RAM. And here you see there are varieties of addressing modes available for this purpose. For example, you can transfer data between a register, any register R0 to R7 to accumulator. It can be bidirectional, or you can transfer data from by using direct mode of addressing, register indirect mode of addressing. You can transfer immediate data, and also you can use register indirect data using stack pointer, which are essentially push and pop operations. These instructions are shown here. So this is your by register addressing, it comes from any one of the register to accumulator, by direct addressing, by register indirect addressing, and by immediate data. So it comes to accumulator, or it can be say from accumulator to one of the registers, or any direct data to one of the registers, any immediate data to one of the registers, and here you can see from accumulator to any direct memory location. And also you can do another interesting thing, direct data to direct data. That means this is what is shown here. So from any RAM, internal RAM to another internal RAM, that data transfer you can do. And of course in this case it takes little longer time because the instruction comprises of 3 bytes and the execution time will be 2 machine cycles, that is 24 clock cycles. And this is essentially the register indirect to direct data, immediate data to direct memory location, and here it is again register indirect, a accumulator to any indirect register indirect memory location by using register indirect addressing, direct data to any one of the memory location by register indirect addressing, and so on. So here essentially data transfer between the accumulator, the any one of the internal registers to internal data RAM by using a variety of addressing modes. And that push and pop operations I have shown here in this diagram. Here push and pop operations, push and pop by using direct addressing. Here the data is coming to the index to the memory location where stack pointer is providing the address. And also you can pop the data where the direct data direct uh, using indirect address, the stack pointer, you can pop the data and can go to one of the memory locations. That means direct address, which is provided by direct addressing. And then you have the exchange instructions which are shown here. These are the push and pop I have explained. And here is the exchange instruction that takes place between any of the registers and direct data, accumulator and any of the registers, accumulator and any direct address in the internal data RAM, and also by you can use register indirect addressing where it can be from between a register and any one of the uh, RAM locations, which is shown here. Exchange A to any one of the register, A and any direct address within the internal RAM, A and any one of the by using indirect addressing any one of the internal RAM, and here it is, you can see here it is the transfer of nibble. That means the lower order byte of accumulator and lower order byte of any of the register indirect addressing, any byte selected by register indirect addressing can be interchanged with the help of this exchange data instructions. So these instructions are shown here, and this is summarized with the help of this diagram. And now after discussing the data transfer instructions, let us focus on the second group of instructions, that is your logic operations, logical instructions or various types of logic operations. The logic operations that is supported by 8051 are essentially AND, OR and exclusive OR. Three logical operations are supported by the 8051, and as you know, the operations performed in these logical operations, this is represented with the help of this truth table. For example, whenever AB is 0 0, then if you perform OR operation AND operation, the result is 0. If you perform OR operation, result is also 0. If you perform exclusive operation, result is also 0. On the other hand, whenever you perform uh, AND operation for 2 bits 0 and 1, then for OR it will be 0, AND will be for AND will be 0, OR will be 1, and exclusive OR it will be 1. Similarly, for 1 0, that corresponding bit for AND will be 0, and for OR will be it will be 1, for exclusive OR it will be 1. Similarly, for 1 1, for AND it is 1, for OR it is 1, and for exclusive OR it is 0. That means you can remember it in this way. For AND operation, only when both the bits are 1, output is 1. That particular bit after operation will become 1. For OR operation, whenever any one of the bits is 1, output is 1. And in case of exclusive OR, whenever one is 0, another is 1, only then the output is 1. So in this operation, that bit by bit logic operation is performed on the byte data, and the corresponding instructions are shown here in this particular diagram, in this particular table, which is summarized. For example, here the AND operation, which is represented by the mnemonic ANL, and logic. Similarly, OR operation is represented by ORL, and exclusive OR is represented by XRL, exclusive OR L. And here you can see the one of the operand is in the accumulator and another operand can be a register, a direct data, uh, or it can be one memory location provided with the help of indirect addressing, or it can be immediate data. That means bit by bit manipulation between these two data, the content of accumulator and another byte which is specified by this addressing mode, or it can be between a data and a accumulator content and a memory location, or it can be immediate data and a direct memory location. These instructions you can see here, this is repeated for OR as well as exclusive OR. This can be represented with the help of a diagram. That means here we always take, not always, in most of the cases we take register A, that means the accumulator, as the source as well as destination. That is why I have put it in the center, and the another byte can be from, say, the internal registers R0 to R7, one of the registers from the register bank that is selected, and similarly it can be for from any one of the register memory location selected by register indirect addressing, register indirect. That means in this case one of the two registers, as you know, R0 and R1 is used as the register pointer registers. Similarly, it can be immediate data, that means immediate data, and that manipulation between that operation and or exclusive or between the accumulator and immediate data is performed and result is stored in the accumulator, or it can be on some direct data, and in this case, as you can see here, you can perform the operation between a direct data that is in the memory location and the accumulator, or it can be operation between accumulator and the direct data, and result can be stored in the accumulator. So, as you can see here, for direct data it can be with accumulator and direct data, or it can be the result is, in this case the result is available in the memory location, and in this case the result is available in the accumulator. You can perform the operation, result can be either in the accumulator or in the memory location internal data RAM, depending on which instruction you are using. So, that is represented by this diagram. Or similarly, for immediate data you can perform these logical operations between immediate data and direct data, and result will be available in the memory location pointed out by the that address provided in the instruction by using direct data. This is the direct address provided here, that is the immediate data and direct data. This is represented by this symbol. So, this picture, this diagram summarizes the various logical operations which are shown in this table. This table shows all the instructions, logical operations, which are essentially two operand. Now, now let us consider the single operand logical operations. Single operand logical operations, which are essentially clear, complement, rotate left. These are the various single operand logical operations are performed. Rotate left through carry, rotate right, rotate right through a carry, or it can be swap instruction, swap nibble. In this case, you are exchanging the lower order byte with the lower order 4 bit with the higher order 4 bit. This can be considered as rotate by 4 bits. So, since these are single operand instruction, obviously the operand will be available in a particular register, and usually the register A is the source and destination of this single operand instructions. Let us see various types of single operand instructions which I have shown in this list: clear, complement, rotate left with carry, rotate right with carry. So these are the various instructions, and the operations are shown in this diagram. As you can see here, in all these cases the operand is available in the accumulator, and after performing the operation, the result is also available in the accumulator, and that's why these are single byte instructions, and the time required is only one machine cycles, that is the 12 clock cycles. So these are single operand instructions, logical operations. Now let us consider various arithmetic operations which are two operand. The arithmetic operations which are in two operand, which are available in the instruction set of 8051, these are addition, and this addition is essentially unsigned. Then add with carry, then subtract with borrow, and multiplication and division. These are the 5 arithmetic operations which are supported by 8051, and this is shown in this particular list. These are the add, addition instructions which can be operated on between a register accumulator and the any one of the registers R0 to R7 in the selected register bank, or direct address data in the internal data RAM provided by the direct address and the accumulator, or indirect address data and the accumulator. So in all these cases, as you can see, two operand instruction, one operand is always in the accumulator, result is also transferred in the accumulator. So these instructions can be represented by the simple diagram where you will have the register A is here, and all these operations, addition with carry, subtraction with borrow, the other operand comes from direct data, that means internal data RAM provided by the direct address, and result is in the accumulator, or it can be immediate data, and third is your one of the registers that you can select from the selected register bank R7 to 0, or you can use indirect addressing also. So register indirect, in this case, as you know, either R1 or register R0 can be used. So this diagram summarizes the various types of arithmetic operations, particularly the addition with carry, subtraction with borrow, and these are the 3 basic operations, and with a variety of addressing modes as it is shown in this table. This is for addition, and these 4 are addition with carry. Again, the addressing mode can be register addressing, direct addressing, register indirect addressing, or it can be immediate data. And subtraction operation is available only in the form of subtraction with borrow. It is not pure and simple subtraction is not available, but you can perform subtraction, pure subtraction by clearing the borrow bit. So and finally the multiplication division. So multiplication division operations is performed in this way, where register A and B, these two take part in the multiplication as well as in division. So the content of register A is multiplied with the content of register B, and result is available in B and A, where the higher order byte is available in register B and lower order byte is available in register A. And as you can see here, the multiplication and division, although the instruction size is only 1 byte, it takes 4 machine cycles requiring 48 clock cycles. Similarly, when you perform division, you divide the content of the accumulator uh, uh, by the divide the content of the accumulator by the content of B, and the quotient is available in the accumulator and the remainder is available in register B. So accumulator will hold the accumulator A will hold the quotient, and the accumulator B will hold the remainder. So these are the various these are the two instructions, multiplication and division available, and both multiplication and division are unsigned, and in both the cases the register A and B register B and A are involved, or you can write AB for the multiplication and division. So this summarizes the two operand arithmetic operations that is available in 8051. So this is the pictorial diagram of the various instruction, and this table shows the list of various instructions available along with the size of the instruction and the time required for execution. So as you can see here, all the arithmetic operations except multiplication and division requires only one machine cycle, that is 12 clock cycles. Now let us look at the arithmetic operations which are one operand. Arithmetic operations which are one operand, which is available, are essentially increment, decrement, increment and decrement. These are the two basic single operand instructions available, which are arithmetic which are single operand arithmetic operations. You can see here increment. You can perform the increment operation of the accumulator, any one of the selected register, or a memory location selected by direct address or by indirect address. Similarly, you can do the decrement operation, and also you can perform the increment operations of the data pointer, which is a 16-bit register, and that operation is done. So these are the two basic single operand instructions available, increment and decrement, and you can pictorially represent it. Since these are one operand, there will be no only one location or register will be involved in it, and for example it can be direct RAM, direct data, on some direct data. That means direct data means it is a RAM location, and you can perform increment and decrement both. Similarly, that register data pointer DPTR, and only increment operations can be performed, as you have seen in the instruction set. Only increment operation can be done on the data pointer, and similarly you can perform the increment operation on register A accumulator, and also you can do increment operation on some memory location using indirect data. So register indirect, where you use the R0 and R1 registers to point to the memory location. So here in this case also you can perform increment and decrement, as you have seen. Here also you can perform increment and decrement, and these instructions are shown here. Increment and decrement on accumulator, on any register, that is your any one of the registers, I have not shown here. Let me draw that. It can be any one of the register. So R7 to R0. So it can be on one of the registers, or direct data, which is shown here, or it can be on internal data RAM pointed out by one of the registers, and finally the data pointer. And in addition to this, there is another single operand instruction that is available in the form of DA, decimal adjust accumulator, which is shown here as DA. What it does, this is provided to support various, it is provided to support the BCD arithmetic. As we have seen, the 8051 processor is essentially performs that unsigned 8-bit processor, but that means unsigned 8-bit data can be processed. Normally it does not process BCD data, but you can process BCD data with the help of the this instruction DA. And what you can do after you perform, say normal, say suppose you have got 2 BCD data in packed form in accumulator, or another BCD data in another register, then you perform addition, and after addition obviously the result will not be in BCD for packed form. So in such a case, if you execute DA instruction, then the result will be converted into BCD form, BCD packed form, which is shown with the help of the operation is illustrated in the here. That what it does, if the lower order 4-bit A0 to A3 is greater than 9, or there is a auxiliary carry coming out of from the 4th bit is 1, then what you do, you add 6 to that lower order 4-bit. Similarly, if the higher order 4-bit is greater than 9, or the carry that is coming out is 1, in either case you add 6 to the higher order 4-bit. If you do that, automatically it can be shown that the BCD data will be if after performing the conventional arithmetic addition, the result will be not be in BCD form, but after you execute this DA, then the result will be in BCD form. Later on I shall explain this with the help of an example when we discuss some programs. Now before I complete our discussion on arithmetic operations, I should also discuss the various flag bits which are affected inside the processor because of the execution of various arithmetic operations. As you can see here, the flag bits are affected only when you execute the arithmetic operations, and also some logical operations. For example, when you perform add, the carry flag bit is set or not set depending on whether there is carry or not. Overflow flag bit is also set or not set. That means overflow flag bit is affected, carry flag bit is affected, and this auxiliary carry that is coming from the 4th bit, D3, that bit is also affected whenever you perform addition, or addition with carry, or subtraction with borrow. In all these 3 cases, these 3 flag bits are affected: carry, overflow, and auxiliary carry. Of course, parity bit is always affected, because depending on the parity bit is set. Then in case of multiplication or division, the carry flag bit becomes 0. However, overflow flag bit is affected whenever you execute arithmetic instructions. Similarly, whenever you execute that decimal adjust accumulator instruction, the carry flag bit is affected, and the carry flag bit is affected whenever you perform these logical operations: rotate right with carry, rotate left with carry, set the carry bit, clear the carry bit, complement the carry bit, and the carry bit, and so on. So these are the bit manipulations instructions. We shall discuss it, and because of this also the carry bits are affected, and or whenever you perform move operations. So, this shows how the various flag bits are affected, and then let us discuss, after discussing the arithmetic and logical operations, let us discuss various control transfer instructions. As you know, in a program, always you will not execute the programs in a sequence from contiguous memory locations. There will be situations where you have to jump to some other memory location. So, there are instructions to perform that. Let us see what are the various types of control transfer instructions available in 8051. The first category is subroutine call and return instructions. Subroutine call and return instructions are available in 8051 instructions, and subroutine call is available in two forms. So, first one is the first one in which your instruction can be only 2 byte, and you provide a short address, 11-bit address, in the form of immediate data. So, immediate data is only 11-bit, and 11-bit data is shifted to the program counter in this way. So, program counter is affected here. So, PC 10 to 0, these bits will hold this immediate data. This data is transferred, immediate data which is provided as a part of the instruction, that is transferred to the bit 0 to 10 of the program counter. On the other hand, the other 5 bits are not affected, it remains as it is. That means PC 15 to 11, these 6 bits are not affected. In other words, by executing these instructions, these 10 bits, 11 bits which are available as immediate data is concatenated with the 5 bits which is available in the program counter, and out of these 11 bits, 8 bit is provided as the second byte, and the 5 bits is provided, remaining 3 bit is provided in the opcode itself, in the most significant bits. And in this case, as you can see, the instruction size will be only 2 byte short instruction, and execution time however is 24 clock cycles or 2 machine cycles. So, whenever you execute this instruction, program counter is incremented by 2, and stack pointer is post incremented, where the lower order byte of program counter is pushed and higher order byte is pushed to the second memory location after incrementing the program counter, and then the program counter, as I have shown, the 11 bits are shifted to PC 0 to 10, and this is called absolute subroutine call. Now, in addition to this absolute subroutine call, you have got another subroutine call, that is called long call. So, in this case, the program counter, all the 16 bits 0 to 15 is affected, is modified, and the 16 bit immediate data which is provided as part of the instruction is transferred to the program counter. So, here you have got 16 bit data, 16 bit data goes to the program counter, and in this particular case the instruction size has to be 3 bytes. So, this address is provided as immediate data, that is transferred to the program counter, and the program counter is as usual pushed in the stack. So, whenever a subroutine call is taking place, you can see here the subroutine call does not push the program status word. In case of 8085, we have seen the program status word is also pushed in the stack. It is not done here. The reason for that is you have already seen the flag bits are not affected that much. Only in case of few instructions the the flag bits are affected by executing various instructions. That's why the only the program counter is posed. However, if you want to post the program status word, you have to use separate instruction for that purpose. Now let us consider the return instructions. You can perform return instruction where you will be performing return, that means the register, that is your program counter will be affected, and it will be coming from the PC. This is 16 bit, here it is 16 bit, but here it was 11 bit. So it comes from the stack pointer by using that register indirect addressing. Register indirect, where the stack pointer acts as the source of the address. So in this particular case, here as well as the stack pointer is post, here it is post decremented. On the other hand, in this case, in the other two previous two cases, the program counter is post incremented, as you can see here. Here it is getting incremented in both these cases, and here it is post decremented. As you can see in the return instruction, the stack pointer is post decremented before you perform pushing the popping the data from the stack pointer to the lower order bit of the program counter or the higher order bit of the program counter. And then it performs it also decrements the stack pointer by 2 after at the end of the execution of the return instruction. Here we find we have got two return instruction. One is simple return, and this simple return is essentially return from subroutine. Whenever you are returning from subroutine, then this particular return is used. And there is another return, this is return for interrupt. Why do you require a separate return for interrupt? The reason for that is whenever you have jumped from a interrupt, you are executing a interrupt service subroutine, there is a internal flag register known as interrupt level flag bit. You know that 8051 has got two interrupt levels. So whether it is in the lower level or higher level, 0 or 1 level, that is kept track with the help of that flag bit. And whenever it is a simple subroutine, then interrupt level is of no importance. On the other hand, whenever it is returned for interrupt, it is essential to restore the previous interrupt level, which was the interrupt level before the processor jumped to the interrupt service subroutine. So it restores the interrupt level. That means apart from performing the same operations that is done for return, it does one additional thing, that is it restores priority level of the return level flip flop. That means there is a priority level, interrupt priority level. That priority level flip flop is restored, which was the situation before jumping to the interrupt service subroutine. That's why 8051 is provided with two return instructions, unlike 8085 where you had only one return instruction. So remember to use RETI in case of return from interrupt and ordinary return whenever you are returning from subroutine. So these are the subroutine calls and return instructions. Then there are a number of jump instructions. Jump instructions can be conditional, or unconditional. There are two types of jumps, conditional and unconditional jump instruction, and the various types of jump instructions are given in this table. And as you can see here, just like the absolute subroutine call, here you have got absolute jump, which is a 2-byte instruction, and the address 11-bit address is pushed to concatenated with the program counter with the higher order 5-bit remains same, lower order 11-bit is modified and with the help of this immediate data, and the program counter is incremented by 2, and it, of course, it has no effect. Ultimately program counter is modified. And similarly you have long jump, like where the program counter is modified by these 16-bit immediate address. So you can say unconditional jump instructions are there, where the register program counter is modified and maybe 15 to 0, all the 16 bits are modified, and it is modified by the immediate data, immediate 16-bit data. So the 16-bit data is pushed in the program counter, and next instruction is taken from that. So jump is taking place. And similarly, this is your long jump, LJMP, or it can be absolute jump, where the higher order byte is concatenated, higher order 5 bits is concatenated, PC 15 to 11 and PC 10 to 0. This is loaded with the immediate data. And here it is 11 bits. So this is your absolute jump. Apart from these two jump instructions, you have got short jump, that is relative. In case of short jump relative, what happens? With respect to the program counter, say you have got the program counter value. With respect to the program counter, you can jump. With respect to the program counter, you can provide immediate data. That immediate data can be, say, plus 127 to 0 to minus 128. So that is added with the program counter. The content of the program counter is added with this immediate data, then jump takes place and program counter is loaded by this value, PC 15 to 0. So this is called short jump, because you can jump within the range. That means if the program counter, say, suppose this is the memory, and the present value of the program counter is this is the program counter. So you can go, say this is your 0000 and this is your FFFF, let us assume. So in this case what you are doing, you can go only within this range. That means it can be minus 128 to plus 127. So within this range it can jump. That is why you are calling it short jump. In the previous two cases, you can jump to any location in this range 00002 FFFF, but in case of short jump, you are restricted to this range plus minus plus 127 to minus 128. That is why we call it short jump. This is your SJMP. And short jump is available where the relative address with respect to program counter jump take place. And also jump instruction is available where instead of the program counter, you can use the data pointer, and the another data comes from the register A. So here you can see here, you can use that base register plus index register indirect addressing to provide the jump address, and these two are content of data pointer and accumulator is loaded into the program counter. And these are the in the unconditional jump instruction. You have got conditional jump instructions, jump 0 when the accumulator is 0, then jump is taking place. This is relative, that is your short jump that takes place with respect to the program counter, or it can be jump not 0, and this is this takes place when that carry flag bit is this jump takes place when based on the carry flag bit. That means compare and jump if not equal. So compare and jump if not equal, this instruction is available, and where you are essentially doing checking a particular bit. It can be a it can be a particular content, say accumulator, or it can be a register, or it can be a indirect memory location. Depending on that, you are it can do the jump, this conditional jump, and then you have got decrement and jump if not 0 instruction, where the selected register is decremented, one of the registers of the register bank is decremented, and then you do the jump if not 0 to a particular, that based on that relative address. Relative address is provided, and based on that relative address you do the jump. That means PC plus that relative address is added and program counter is loaded. So in case of these jump instructions, as you can see, all these instructions require 2 machine cycles. So these are the various types of jump instructions which are available in 8051. Then finally you have got bit manipulation instructions. As I mentioned earlier, in case of microcontrollers, bit manipulation plays a very important role, and 8051 has been provided with a very rich set of bit manipulation instructions. And let us see what are the various types of bit manipulations instructions available in 8051. The bit manipulation instructions which are available are clear, that means that mnemonic is CLR and C bit. That means it can clear that carry flag bit or any particular bit within the data RAM or the special function register. Or you can perform set operation, you can set a particular bit, and mnemonic is set B. It can be also the carry flag bit or any bit of the memory location or the selected bit. We have already discussed which particular part of the RAM you can access for bit manipulation, and also which special function registers can be also selected for bit manipulation, that we have already discussed. Those bits can be cleared or set, or also you can perform complement, where the mnemonic is CPL. You can do the same thing. Then you can perform AND operation, that means selected bit and the carry flag bit, that means C carry flag bit and the selected bit. Here you see that carry flag bit is acting as some kind of accumulator. Similarly, you can perform OR operation, ANL, ORL, OR operations, carry flag bit and the selected bit. And then you can perform data transfer, and that means you can transfer a particular bit to a particular selected bit, say by using move instructions. That means between the carry and the selected bit, data transfer can take place by using move instructions. Then you can perform jump if carry set, JC, and here you are using relative addressing, that address is provided by relative addressing. Then jump if bit set, a particular selected bit is set of the memory locations or the special function registers. Here it is JB. Then you have got instruction like jump if carry not set, JNC, and in both the cases the address is relative. Here also it is relative. Then of course you have to provide the bit, which particular bit, that address also has to be provided here. Then you have got jump if bit not set, that means JBC. Here you provide the bit to be selected, and also the relative address. Then finally, you have got jump if direct bit set JBC, sorry, here it will be JNB, here it is JBC, and bit and relative. Jump if direct bit set and then clear. This is the instruction. So these are the various types of bit manipulation instructions which are available in 8051. Let us have a look at the list. Here we see we have got that clear carry flag bit, clear a particular selected bit, that address is provided here, set that carry flag bit, set a particular bit, the address is provided here, complement carry flag bit, complement the selected bit, AND operation between a carry and the selected bit, AND operation between carry and complement of that bit, OR operation between carry and the selected bit, OR operation between carry and the complement of the selected bit, and move operation between the carry. So you can transfer a selected bit content to the carry flag bit. You can also transfer the content of carry to the selected bit location. Then jump carry relative by using relative address. Jump if this bit is set, then if bit is equal to 1, then you do the jump operation to the relative address. And whenever jump, these two are the same thing. Here jump not carry, here it is jump, that means if the in this jump will take place if the carry bit is 0. Here it was carry, here the carry bit was 1, in this case the carry bit will be 0, rest of this thing is same, that means he is 0, rest of the thing is same. Here also that bit will be 0, rest of the thing will be same. Then this particular instruction, as I have told, jump if direct bit set then clear, that means if this bit is set 1, then jump takes place, and after doing that bit is cleared. So here you are doing two things, you are taking decision based on that bit, if it is set then jump is taking place, and also before jump is taking place you are clearing that bit. This type of instructions may be required in future. And here you can see here some of the instructions can be executed in one machine cycle requiring 12 clock cycles. However, some instructions will require 2 machine cycles requiring 24 clock cycles. So we can summarize today's lecture by saying that we have discussed various types of instructions provided by 8051, the data transfer instructions, logical instructions, arithmetic instructions, and control transfer instructions. In the next lecture, we shall discuss how these instructions, that is the vocabulary of 8051 machine, can be used to write useful programs. Thank you.